In section 6.6, we'll be discussing integration with substitution. So the role of integration by substitution is similar to that of the chain rule when we were taking derivatives. So let's recall the chain rule. So if we're given that y is f of u and u is g of x, in other words, we just have f of g of x. When I take the derivative of the outside, I leave the inside the same, then I multiply by the derivative of the inside. And so if I want to do an antiderivative, that just means taking this and going backwards. So if I integrate f prime of g of x times g prime of x, which is what I have here, notice I did add on this dx here, that would give me f of g of x. Notice I took off the prime, so the antiderivative of f prime is f at g of x, and then plus the constant. Now you might get confused because this g prime of x seems to have disappeared, but really what's happening, we're going backwards. So that g prime of x was something we added on when we took the derivative, right? We did f prime of g of x and then times g prime of x. We added this other part that we were multiplying. And so if we're going backwards, then essentially we are taking that away. So that is the derivative of the inside part. So when I take the antiderivative again, it's the antiderivative of the outside, leave the inside the same, plus a constant. I have to have that g prime of x dx though. It's kind of my passport to being able to use substitution. So the derivative of the inside needs to be present in my integral in order for me to be able to integrate this using essentially the backwards chain rule. So we're going to use u's instead of g of x. So a lot of times you'll see this called u substitution. And so what you'll want to have is an f of u and then your du dx, which is your derivative of u dx. And that will be the antiderivative of little f, which a lot of times we say is big F of u plus c. So let's actually test this out. In example 1, we have the integral of 2x times x squared plus 1 to the 4th dx. Now, a lot of times it's not going to be as obvious what rules you're going to use when you're integrating this. You most certainly could do like we did in 6.5 and expand this, but if this is to the 4th power, that's going to be a lot of work that we don't want to do. So essentially, one of the ways that you're going to know that you might need to use substitution is by looking at something, and if you would see this and say, there's something inside of something else, or in other words, I would use chain rule to take the derivative of this, then you will use u substitution to find the antiderivative. So let's focus first on what the inside is. My inside function, u, is x squared plus 1. So that's what I'm going to call my u. U equals x squared plus 1. Now, that's my inside function. So that's like my g of x here. And I need to make sure that the derivative of that inside function is present. So I'm going to write this as du. The derivative of u, the derivative of x squared plus 1, is 2x dx. Now, I prefer to write it this way. You could write it as du over dx equals 2x, but I just moved the dx to the other side. Now, I want to pay attention, do I have a 2x dx in my problem? 2x dx, I see I have a 2x and a dx. They are not often right next to each other, but I do notice I have that g prime here. And so then I'm going to rewrite this. This is the step that's called a u substitution. So I'm going to replace my x squared plus 1 with a u. So this is going to become u to the 4th. The 2x dx is combined into a du. So I have the integral of u to the 4th du. Now, this u just acts like a dummy variable. I'll integrate like normal. So the antiderivative of u to the 4th would be u to the 5th over 5 plus c. That's not my final answer, though. I don't want to leave my answer in terms of u. I want to have it with x's. So then I just need to replace my u with an x squared plus 1. X squared plus 1 to the 5th over 5 plus c. And if I wanted to check my answer, I would take the derivative. So I'd have 5 times x squared plus 1 to the 4th over 5. And I'd have to multiply by the derivative of the inside, which is 2x. So notice that I would get the same thing that I had for my integrand here. So once again, we're paying attention to what's inside, and then I'm looking for the derivative of the inside to be present as well. So in part B, I have the integral of 3x squared square root of x cubed plus 1 dx. So I'm going to be looking at my inside function first. So I see that x cubed plus 1. That's what I'm going to try to make my u. U equals x cubed plus 1. Let's check then to see if our du is present. Du, the derivative of x cubed plus 1 is 3x squared dx. Do I have a 3x squared dx? I do have a 3x squared dx. And so I can go ahead and make this substitution. So notice I'm going to rewrite this with u's first with my integrals. I want to rewrite the square root as u to the 1/2. The 3x squared and the dx are combined into my du. Remember, du is equal to 3x squared dx. Now I'm ready to take my antiderivative. So this is u to the 3/2, but then I have to divide by 3/2 or multiply by 2/3 plus c. And so then my antiderivative is 2/3. Plug back in my u, x cubed plus 1 to the 3/2 plus c. On part C, we have the integral of secant squared x times tangent x plus 3 dx. It might be harder here for you to decide what your u should be, because this secant is being squared, so you could think of secant as inside, and tangent x plus 3 is in parentheses. And so what you have to remember is that we have to have the derivative of one part there. So you have to think to yourself, is secant or secant squared the derivative of tangent x plus 3, or is tangent x plus 3 the derivative of secant squared x? And what is true is that secant squared is the derivative of this tangent x plus 3. So if I make my u tangent x plus 3, then my du is just secant squared x dx. So my u is this part, tangent x plus 3. My du is the rest of this secant squared x dx. So remember your trig derivatives there. So this will become the integral. This is just u in parentheses, u to the first power. So just u, du. I take my antiderivative. That'll be u squared over 2 plus c. And so my final answer is tangent x plus 3 squared over 2 plus c. Now, sometimes our du is not going to be a perfect match like it was in the last 3 examples, so we might need to figure something else out. So essentially what we're going to do is just compensate. As long as our difference is only by a constant, then we can just kind of adjust the integral or balance it out with a constant coefficient. So let's check this out. In number 2a, we have the integral of x times x squared plus 1 to the 6th dx. So again, I'm going to pay attention to my inside function. So I'm going to call x squared plus 1 my u. U equals x squared plus 1. My du is, so notice I'm not going to pay attention to the integral right now. I'm just taking the derivative of this u. U is x squared plus 1. The derivative of that is 2x dx. And so I want to look and see, do I have a 2x dx in my integral? I don't. I have an x dx. So I have this part here. And so in order to make an even substitution, I need to solve this equation for the x dx. In other words, I just need to divide by 2. So I'd have 1/2 du is equal to x dx. And then I can make an even substitution for x dx. That's just 1/2 du. So when I rewrite my integral now, I'm just going to put the 1/2 out in front. You can leave it inside the integral, but it's usually easier to just put it out in front. This is my u to the 6th du. Okay, so my du, I had 1/2 du, that was equal to x dx. And now I can take my antiderivative like normal. So 1/2 u to the 7th over 7 plus c. So when I rewrite this, I could rewrite it as 1 over 14 x squared plus 1 to the 7th plus c. So again, we just compensated there. As long as our du is different only by a constant, we can do that. In part B, we have the integral of square root of 2x plus 1. So my u is going to be 2x plus 1, my inside function. My du, the derivative of 2x plus 1 is 2 dx. Do I have a 2 dx? I do not. I have just a dx. And so I'm going to need to divide by 2. So this integral will now become 1/2 the integral of u to the 1/2 du. Take my antiderivative, 1/2 times u to the 3/2 divided by 3/2 or multiplied by 2/3 plus c. Final step is to plug your u back in. So the 2's cancel out here. I have 1/3, 2x plus 1 to 3/2 plus c. All right, in part C, same idea. It might be a little bit harder when we have more terms to decide which function is my u and which one isn't. Notice the radical here, so a lot of times our u will be under a radical. Also, since we have to take the derivative, a lot of times our u will have a higher degree. So I'm going to say that my u is this 4x cubed minus 5. U equals 4x cubed minus 5. Let's take the derivative of that. The derivative is 12x squared dx. Do I have a 12x squared? No, I have a 7x squared dx. Really, I'm just going to focus on that x squared dx. And so if I divide both sides here by 12, I would just have x squared dx. But if I want 7x squared dx, then I'm going to just multiply both sides by 7. And then I can do that even replacement. You could also just factor the 7 out in front of the integral to begin with and make that substitution. So when I rewrite my integral, it will be 7/12 times the integral. This is a square root in the denominator, so u to the negative 1/2 du. So the 7/12 comes along. Antiderivative of u to the negative 1/2. So I'm going to add 1, that's u to the 1/2. Divide by 1/2 is multiplying by 2 plus c. So that would give me 7/6 times 4x cubed minus 5 to the 1/2 plus c. So you can perform integration by substitution for more complex trig functions as well. So this is when you see essentially anything inside of trig function besides just an x. So here I have sine of 2x. There are no parentheses here, but 2x is actually inside of the sign there. And so 2x will be our u. Our du is 2 dx. We don't have a 2, so we're going to divide by 2. So when I rewrite this, the sign is my outside function. It's not part of my u or the derivative of u. So I'm going to rewrite this as 1/2 sine of u du. And sine is something I know how to take the antiderivative of. So the derivative of what function would give me sine? That would be negative cosine of u. Remember that the antiderivative of sine is negative cosine. The derivative was positive cosine. Last step, I want to replace that u. Negative 1/2 cosine of 2x plus c. And again, as a reminder, if you need to check your answer, you can take the derivative and see if you get your integrand. In part B, we have cosecant squared of theta over 4 d theta. So again, I'm going to focus on that inside part for my u. U is theta over 4. You can also think of that as 1/4 theta. So it's just a constant times theta. So when I take my derivative, it's just 1/4 d theta. I don't have a 1/4 d theta here, so I'm going to have to multiply both sides by 4. 4 du is equal to d theta. So now when I make my substitution, I'm going to have 4 times the integral of cosecant squared of u du. So I'm replacing the theta over 4 with my u. Now I can take my antiderivative. The antiderivative of cosecant squared is negative cotangent of u plus c. And then don't forget to plug your u back in. In number 4, we have sine squared of 3x times cosine of 3x. So you might think that your u is 3x. So if u is 3x, the derivative of that is 3. That would just make this sine squared u times cosine u du. Have to divide by 3 here. But I still don't know how to find that antiderivative. So I'm going to have to make my u something a little bit bigger. And to help you here, let me try to get this erased. You might want to rewrite that sine squared. So think about like when we were taking derivatives, what we would have to do. We would rewrite this as sine of 3x quantity squared times cosine of 3x. dx. And so now you might be able to tell your inside function is actually this whole thing sine of 3x. Because I know then, if that's my u, sine of 3x, the derivative of that is going to involve a cosine. So the derivative of sine of 3x is cosine of 3x times 3 dx. And so I have the cosine of 3x there. I just need to divide by the 3. That's the piece I'm missing. So I'm going to have 1/3. The sine of 3x is my u squared du. And now I can integrate. So 1/3 times u to the third over 3 plus c. And so I would get 1/9 sine of 3x cubed plus c for my answer there.